Hello, welcome to another module in this massive open online course on principles of CDMA, MIMO, OFDM, wireless communication systems. What we have seen in the previous module, we had seen how we can combine the signals received in a multiple receive antenna system employing MRC, that is maximal ratio combining. What we are going to do now is we are going to look at an example of an MRC system of a maximal ratio combiner. So, what we want to do is we want to look at example of a maximal ratio combining system. So, what we want to do is want to consider a system with a transmit antenna and a receive antenna and two receive antennas as we had seen previously, and we have two receive antennas and we had denoted the fading coefficients between the transmit antenna 1 and receive antenna 1 by H1, transmit antenna 1 and receive antenna 2 by H2. And now, in this example, let us consider H1, the complex fading coefficient equals 1 by square root of 2 plus 1 by square root of 2 j. This is a simple example, and we are considering H2 equals 1 by square root of 2 minus 1 by square root of 2 j, and therefore, we have these two fading coefficients H1 which is given as 1 by square root of 2 plus 1 by square root of 2 j, H2 which is given as 1 by square root of 2 minus 1 by square root of 2 j. Therefore, we have Y1 equals H1 x, that is 1 by square root of 2 plus 1 by square root of 2 j times x plus n1, and we have Y2 equals 1 by square root of 2 minus 1 by square root of 2 j times x plus n2. And further, what we are going to assume is that in this example we are going to set, let us say, expected value of magnitude n1 square equals expected value of magnitude n2 square equals sigma square, which is equal to a half, and in dB terms this is also 10 log 10 of half equals minus 3 dB. So, we are assuming a noise power of minus 3, that is noise power of half per antenna or noise power of minus 3 dB at each antenna, right. That is, noise elements N1 and N2 have equal power sigma square, which is equal to half or minus 3 dB. Okay. And now, what we want to do, and now if we know, remember we represented this as a vector, that is y1 y2, y1 bar y2, y1 y2, or denoted by vector y1 is the vector h bar, which is h1 h2, which in this case 1 by square root of 2 plus 1 by square root of 2 j, 1 by square root of 2 minus 1 by square root of 2 j times x plus n1 n2, that is representing this as a vector, we have y bar equals h bar x plus n bar. And now, therefore, the MRC, optimal MRC beam forming vector, the optimal beam forming vector or the optimal maximal ratio combining vector is equal to h bar divided by norm of h bar. And now, we have seen our vector h bar, this is given by this vector, and the norm of vector h bar, we know that the norm of vector h bar equals square root of magnitude h1 square plus magnitude h2 square. Now, our vector h bar, we know that h bar equals 1 by square root of 2 plus 1 by square root of 2 j and 1 by square root of 2 minus 1 by square root of 2 1 by square root of 2 j, and norm of h bar square equals square root of magnitude h 1 square plus magnitude h 2 square, but magnitude h 1 square is sum of squares of real and imaginary parts, that is half plus half, plus magnitude h 2 square is again the sum of the squares of its real and imaginary parts, which is half plus half, which is equal to square root of 2, right. So, norm h, so norm h bar equals 2, and therefore, my w bar equals h bar divided by norm of h bar equals 1 by square root of 2 times 1 over square root of 2 plus 1 over square root of 2 j, 1 over square root of 2 minus 1 over square root of j divided by square root of 2. So, this is my optimal maximal ratio combining. So, this, now let me point out this is the MRC vector, this is the maximal ratio combining vector, or also the MRC vector, that is h bar divided by norm h, and we have shown that norm h is equal to square root of 2. Therefore, h bar divided by square root of 2 is the optimal maximal ratio combining vector. And now, what we also show, now what we want to derive is, we want to derive the SNR. The SNR, remember, equals norm w bar Hermitian h bar square p divided by sigma square norm w bar square. And now, we also know that basically when, now we also know, let us compute this quantity w bar Hermitian h bar equals, well, 1 over square root of 2 times, we have to take the complex conjugates, 1 over square root of 2 minus 1 over square root of 2 j, 1 over square root of 2 plus 1 over square root of 2 j times h bar, which is 1 over square root of 2 plus 1 over square root of 2 j, 1 over square root of 2 minus 1 over square root of 2 j, which is equal to 1 over square root of 2 times 1 over square root of 2 minus 1 over square root of 2 j times 1 over square root of 2 plus 1 over square root of j. So, this is again half plus half plus another, you can see half plus half, which is equal to 2 divided by square root of 2, which is equal to square root of 4. So, w bar Hermitian h bar equals square root of 2, which means magnitude w bar Hermitian h bar whole square equals square root of 2 whole square equals 2. Further, if you look at norm of w bar square, norm of w bar square equals, well, this is equals magnitude w bar, magnitude w1 square plus magnitude w2 square, which is equal to half into half plus half plus half plus half, and this is equal to half times 2, which is equal to 1, and that is what we expect, because we have normalized w bar to unit magnitude. When we considered w bar equals h bar divided by norm of h bar, we have normalized, already normalized w bar to unit magnitude, and therefore, we can see norm of w bar square is equal to 1, and therefore, the SNR equals p times w bar Hermitian h bar whole square divided by sigma square times norm w bar square, which is equal to p times 2 divided by, now sigma square as we had seen previously is half, norm W bar square is 1, therefore, this is equal to 4 p, and therefore, what we have is SNR equals 4 times p for this system with maximal ratio combining. This is for MRC with maximal ratio combining. This is for the system with maximal ratio combining, right. So, what we have done is we have looked at a simple example and we have considered the channel coefficients H1 and H2, and what we have done is we have derived the SNR of this system with maximal ratio combining, and we have demonstrated that it is equal to 4 times p. And now, what we want to do is a small point, we want to extend this to L antennas. Right now, we have considered a scenario with 2 antennas only, we want to generalize this to L antennas. So, we want to generalize it, generalize MRC. So, let us generalize the concept of MRC to L antennas, and that is fairly simple, as you might have already realized. If I have a transmitter and I have a receiver and I have a single transmit antenna, and now instead of having only 2 receive antennas, let us say I have multiple receive antennas, and the various channel coefficients I am going to denote by H1, H2, so on up to HL. So, the channel coefficients are H1, H2, HL. So, what we are saying is the coefficient between transmit antenna and receive antenna 1 is H1, coefficient between transmit antenna and receive antenna 2 is H2, so on. The coefficient between transmit antenna and receive antenna L is HL. So, instead of, so previously where we had 2 coefficients or we had 2 antennas, we had 2 coefficients. Now, we have L antennas, an arbitrary number of antennas L, and therefore, we have the correspondingly L channel coefficients H1 to up to HL. And now, I can represent the system model, the vector system model for this system as Y1, Y2, YL equals H1, H2, HL x plus the vector noise vector N1, N2, NL. So, I have y bar equals H bar x plus N bar. And similarly, for the noise one can assume, as we have done previously, that expected each Ni square equals sigma square, that is each noise has power sigma square, that is noise power equals sigma square. Further, we can also assume that the noise on any 2 antennas to be uncorrelated, that is expected value of Ni Nj equal to 0 for all I not equal to j, that is noise on any 2 antennas is uncorrelated, that is noise on any pair of antennas is uncorrelated. And now, we can perform the combining at the receiver as y tilde equals W1 conjugate Y1 plus W2 conjugate Y2 plus so on WL conjugate YL, which basically one can now write it in vector form as equals W bar Hermitian Y bar, which is basically equal to W bar Hermitian Y bar equals H bar x plus N bar, which is equal to W bar Hermitian H bar plus x plus W bar Hermitian N bar, and this is the signal part. Now, again this is the signal part, and this is the noise part, and therefore, for maximum signal to noise power ratio, for achieving the maximum signal to noise power ratio, one can choose MRC or maximal ratio combining, choose MRC that is maximal ratio combining as W bar equals H bar divided by norm H bar, which is basically 1 over norm H bar times the vector H1, H2 up to HL, where the quantity norm H bar, you should be familiar with this by now, norm H bar is equal to square root of magnitude H1 square plus magnitude H2 square plus magnitude HL square, and also the SNR with maximal ratio combining equals norm H bar square times P divided by sigma square. This is my SNR with maximal ratio combining, which is equal to P times magnitude H1 square plus magnitude H2 square plus so on up to magnitude HL square divided by sigma square. So, what we have derived is we have derived the SNR with maximal ratio combining in an L antenna system. So, what to summarize in this module, we have seen an example of maximal ratio combining in a system with 2 receive antennas, and we have generalized the concept of this maximal ratio combining to a system with L receive antennas, in which we have said that the MRC beam for MRC vector combining vector W bar equals H bar divided by norm H, and also the associated SNR for maximal ratio combining is P times norm H square divided by sigma square, which is P times magnitude of H1 square plus magnitude H2 square, so on so forth until magnitude HL square whole divided by sigma square. So, this is the concept of maximal ratio combining to extract diversity, that is, as we said, we began this discussion because of diversity, that is, we wanted to employ diversity in a system with multiple antennas to basically improve the bit error rate performance of the system. And in subsequent modules, we are going to see how this diversity, how having multiple receive antennas in reality enhance or improves the performance by decreasing the bit error rate. Thank you very much.